I'd like to introduce our speaker. Lionel Lacroix is from Brock University, and Lionel is going to be talking to us about two different things. One is mathematics practices in construction trades, and the comparison with school mathematics. And he's also going to talk about how he's had interviews with some of these trades folks on how to read a measuring tape. So,
thank you very much.
Thanks.
Well, it's a delight to be here. I was told when I did my defense, this is the day when you get to share your stuff and have people there who are interested in hearing you. So this is like a bonus. Thank you all for coming, and thank you for inviting me, Anne. Just to give you an overview, I use cultural historical activity theory, and I'm not going to go into theory. I want to give you some examples, some interesting juicy bits from my doctoral work. And if you're interested, you'll read more. Trying to do theory and analysis and make sense of that in a 40-minute session is a recipe for disaster. So I'll just give you a bit of a sampling of some of the ideas and analysis that I did. So the outline is as follows. We'll start with a brief background to my research. Then there's actually, it's like a two-part presentation. The first part will look at math practices in workplace training and compare that with school mathematics. Then we'll look at, do a microanalysis of some of the social and semiotic processes involved in the microgenesis, that is the formation of mathematical thinking of a pre-apprentice in the pipe trades who is learning to read a measuring tape. Now in Canada, metric was mandated in schools across the country some decades ago, and this fellow went to school, as did all other kids his age, only learning the metric system. So when he came to the pipe trades, piping is of course manufactured according to American standard specifications, he encountered fractions of an inch for the first time. And so the focus is a 33-minute interview, a 33-minute tutoring session. I was the tutor, and we sorted out the process. So I'll highlight some of the processes that are part of that. And the last part is a discussion for teaching. Now I'm going to, as a teacher, ask you to put your thinking caps on, and I'd like you to be imaginative and frame this in terms of your own work and your own experiences, and I'm looking for you to give me suggestions. I will offer some implications for teaching, but I'm looking as much for some ideas for you in terms of how you see this work and how you see it maybe applying in other areas or in your own work. So just an introduction to the project. The funded project was the UBC Workplace Numeracy Project. We worked in conjunction with the BC Construction Skills Trades Improvement Council, known as SkillPlan. SkillPlan is a trade union and management sponsored initiative in the construction trades in BC that serves workers and apprentices with issues around literacy and numeracy. The folks at SkillPlan do everything from tutor apprentices at the local coffee shop to developing course materials to be used across various workplace training programs. So they do a wide variety of things, and they were our partners in the funded project, and they were our vehicle in and our pilots in terms of getting into programs where there was a need, and certainly getting our foot in the door in apprenticeship training programs. The research team at UBC was Lyndon Martin. Dr. Lyndon Martin was in charge of the program. I did all the field work over 2 years, and Lyndon and I worked very closely on the project. The goals of the funded research project were to identify issues around mathematics learning in apprenticeship training. For a lot of apprentices, the mathematics component of the accreditation testing is an obstacle, and so our goal was to bring a mathematics education lens to try and bring some ideas to that, and really explore it. It's an area that hasn't been explored in depth by math educators. The field work took place over 2 years. I visited a number of apprenticeship training programs. These were run either at trade union schools or at a community college, BCIT, in Vancouver. And I visited for shorter durations of a few days, typically electricians, HVAC, heat, ventilation, air conditioning technician program, heat and frost insulation program. There was one more. I also shadowed some HVAC workers on the job for some days, and then I hunkered down for extended periods of time in all 3 levels of ironworking. So for the first level of ironworking is a 6-month program. Levels 2 and 3 are a couple of months each, and the way the apprenticeship program is structured is that students go to school and then are out in the workforce for 8 to 10 months, and then come back for a couple of months and go back out. And so I visited those classes whenever they were doing math in the shop or in the classroom, and asked students to explain to me what they were doing, and I videotaped what took place. Both in the classrooms and in the shop. I also sat through an entire level 4 plumbing apprenticeship course, which focused mostly on gas fitting and preparing students for their final exam with the Ministry of Labor. And 2 sessions, 2 8-week sessions of a pre-apprenticeship program in the pipe trade. So it was organized by the local plumbing union, and it prepared students to go into a number of different pipe-related trades, and covered most of the, because it's not officially part of the apprenticeship training program in British Columbia, the instructor aimed to address the kinds of things that they would be doing in levels 1 and 2 to give them levels 1 and 2 of the formal program, and give them a head start on that, as well as some safety and basic shop skills so they would be ready to enter the workforce. And it was the second of those 2 that was the focus of my more in-depth analysis. So my dissertation, as I said, focused on a 33-minute, well, 2 things. I looked at apprenticeship training in general, and did some analysis there that I'll share with you today, and then did a microanalysis of this 33-minute episode. And that 33-minute episode of working with a single student was a particularly rich and sustained instance of learning from start to finish, and was unique in the data set. So it provides some good insight to the processes involved. Now, just to compare math activity in the construction trades and construction trades training with that of elementary and secondary school, you know, there are, I use cultural historical activity theory, and we need not get into that in much detail, but that directs us to look at certain things and pay attention to certain things as we try to understand the whole of the activity that's happening. But before we do that, I just want to share with you some examples of workplace mathematics tasks that I encountered in the various programs. So in the pre-apprenticeship program, pipe fitting with screwed pipe, when you put pipe together, the thread goes in the other one, so you have to accommodate that in determining the length that you cut your pipe. So there are calculations with fractions of an inch involved for various, and they differ for different sizes of pipe. Rolling offsets and parallel offset calculations. Here we have in 3 dimensions, you know, a pipe coming in and a pipe going out, and the calculation is the length of the pipe to join them. However, with threaded pipe, the fittings come in 45-degree and 22.5-degree. 22.5 is kind of unusual, but 45-degree fittings. So in that case, you'd have to extend the run to make a 45-degree connection at each end. Not the case with bent pipe. Parallel offsets uses a fair bit of Euclidean geometry to, when pipes need to bend, and turn a corner and maintain the same distance apart for installing insulation around the pipes or for supporting them. There are some calculations involved there. Some other examples, unit of measure conversion. One that was particularly difficult in a number of apprenticeship programs was converting between feet, inches, and fractions of an inch to decimal feet. So if you're calculating area or cross-section, that would be needed. Flow demand and piping requirements for configurations of multiple appliances or plumbing fixtures. There's a bit of a logistics in terms of how best to, if you know where these appliances are and they have to be joined by pipe that has to either take something to them or take something away from them. There was some logic and some calculations to do about optimizing the installation of the pipe involved. Mass calculations for objects to be lifted or supported. The apprenticeship program I forgot earlier was the operating engineers, the crane operators. I visited their program as well. They, the iron workers, and the plumbers all needed to be able to reliably do mass calculations for part of their work. Now, comparing different parts of the two activities, the subjects, motives, and goals. Well, in workplace training, the participants were there because they wanted to join the workforce in a particular capacity, or they were already apprentices in a particular trade. They had an identity as a member of that community. And their goal, they were there doing the mathematics so that they could do their job. Comparing that with school, individuals' goals, the goals of individuals are not aligned necessarily with one another, and often not necessarily aligned with the goals of the teacher, whose goals are mandated by prescribed curriculum. The goal of learning mathematics is often focused on meeting the demand of pencil and paper evaluation. Objects of activity. The mathematics containing activity of workplace training consists of a relatively small number of well-defined forms of workplace production. The mathematics is subordinate to this end. Efficiency and reliable mathematics methods are the focus, and as the instructors would say from time to time, time is money. So it was about getting an answer reliably and efficiently. In school, the object of activity is often generalizable and more abstract methods for application in a variety of contexts. Our students in high school are going to any number of places after high school, and we want to prepare them for any of those possible contexts. Beliefs about mathematical objects. In the trades, in the pipe trades in particular, the only numbers that matter are numbers to 1/16 of an inch. Nothing else is part of their thinking. It serves no purpose. Where in school we deal with rational and irrational numbers, and it's a different way of thinking about numbers and relating to numbers. The relationship, a relation of sensuous / bodily / life experience to mathematics practice. For many skilled workers, many measurement values have a feel to them. These values relate to physical objects they have grappled with, and measurements and calculations often involve an element of feel. Whether it be that physical feeling of how it's going to fit together if you adjust the dimensions a little bit one way or the other, but also picking the darn thing up. On one occasion, an iron worker said there's no way that's 200 pounds, because he knew he could go over and pick up at least one end of a 200-pound beam, a steel beam, and so he brought that to his experience. In school, math problems are often dealt with in the abstract, and when application-type tasks are used, students often have little experience upon which to make sensuous connections. Too often, real-world problems consist of window dressing, that is, abstract and unrealistic situations made to look authentic. Norms or conventions of mathematics practice. Norms in workplace training and the workplace tend to be context specific. They're different from trade to trade. In plumbing, as I said, rounding to the nearest 1/16 of an inch is a norm. It's the norm to use whatever means is possible to arrive at a mathematical solution, and there are often norms around acceptable tolerances, what's close enough, and in different contexts, and allowing margins of error. When you're an iron worker and you're hoisting beams in the air and assembling a skyscraper, you err 10% on the side of caution in case there's some wear in the slings that are holding it up. Compare that with school classrooms. As I said, norms tend to be context specific, and because we're generalizing in school mathematics, we don't talk about those kinds of norms that you would find in applying mathematics. But there are some norms of school mathematics. Check your work, your answers with the back of the book, show your work, put the dates on the top of each page, and underline titles. Conceptions of truth, mathematical truth. In the workplace, does it fit? Does it work? Does it do the job? In school mathematics, we often rely on standard kinds of proof and writing things up in certain and particular forms. Inquiry and problem solving. In the workplace and in workplace mathematics, the problem is solved when you're done. If you don't have an answer, you're just not done. It's not wrong. Whereas in school mathematics, often we use pencil and paper solutions. We don't rely on physical objects as part of our thinking process. If a student doesn't have the solution, he or she is mistaken or at fault for not having completed his or her work. And the last point, semiotic resources and artifacts used, including technology. In the workplace, the tools of the trade are often used as part of the thinking process. To give an example outside of the construction trades, in my dad's machine shop, he would use the digital readouts of his milling machine to find the center of a piece of steel. He wouldn't have to measure it out with a ruler and divide the length in half. He could use his tools for some shortcuts. I was shown a trick for subtracting dimensions using a measuring tape. If you have 4 feet and you want to take 5 7/8 off, you measure out 4 feet, fold the measuring tape back onto it to 5 feet, count the amount you're taking off, and then you can read the length you require. So there are ways of thinking and reference to use in doing mathematics in the workplace. At school, this would be cheating. Now, can you even imagine doing measurement outside of school without a ruler? Now, I've pondered that from time to time. I can't imagine that. Most of the measuring that kids do in school is out of the textbook. The drawings are given. It's without a ruler. So they're very different kinds of activity. So, from the perspective of cultural historical activity theory, all of these things mediate and are themselves mediated by mathematical activity, including thinking. Now, why is it helpful to recognize school mathematics thinking and practice, workplace mathematics thinking and practice and that of school mathematics to be separate genres? If we come to workplace mathematics with our academic mathematics hats on, then mathematics of the workplace is just a watered down or poor cousin to school mathematics, but it serves a different purpose. And it serves that purpose perfectly well. So I think it behooves us to allow there to be more than the way to do mathematics that we come to know and value. And to understand that in different contexts, mathematics takes a different form. And I use the word genre to describe that. So we want to avoid a narrow focus when we teach mathematics in the workplace. It's not just the computations on the page. It's doing mathematics on the job, using the tools, doing it in context, developing that feel for the mathematics. And related to that is ensuring meaningful connections in workplace training to the applications of workplace practice. And lastly, when we analyze both learning and programs of workplace mathematics, if we're looking at it through the lens and looking at students through the lens of school mathematics, we can only say they can do the math or they can't. We really don't have a means. I'm thinking about when we look at math as just being pencil and paper. We're losing an opportunity to look at the way they do math and move them forward in doing mathematics in a way that's appropriate for the workplace. Now, we'll now look at the pre-apprentice learning to read his measuring tape. So we're going to be looking at the social and semiotic processes involved in becoming aware of cultural mathematical objects. Now I'll explain this. Lewis Radford is a math educator who works from a cultural historical activity theory perspective, and he was, I drew upon his work, and I was lucky to have him as my mentor through my doctoral research. There are two, well, his theory is called the theory of knowledge objectification, and to explain, objectification refers simply to the process of an object, a mathematical object or a cultural object becoming an object of our awareness. Okay? When we, and semiotic means of objectification refers to the use of various forms of signs, whether it be language, pointing, inscriptions, to draw the attention of another or to sustain our attention on a cultural object. So it's the dance of the teacher, or the dance that we do ourselves to help sustain our thinking and attention on particular things. Now, the pre-apprentice, I'll refer to him by his first initial, C, was learning to read fractions of an inch on his measuring tape. His particular measuring tape was marked to 32nds of an inch to a foot, and 1/16 of an inch thereafter. This was about a week into the 8-week program. He had a threaded pipe configuration to build, and he and his colleagues were in the shop having built their pipe configurations, and they didn't align properly, and the group of them were discussing what to do next and how to redo the project appropriately. And based on my observations there, I noticed that C was not reading his measuring tape correctly, and so I ushered, well, after a brief conversation in the workshop, I ushered him into a quiet spot in the classroom, and we sat down and spent in total 33 minutes talking about this. So the first clip is 3 minutes into the session. We've just sat down at the table in the workshop. Now, in this part of in this first clip, we're going to see this clip twice. We're going to see the first. This is clip 1. We're going to see the first part of clip 1, and I want you to attend to the different pointing gestures that I make and the sweeping gestures to distinguish between the region of the measuring tape below 12 inches and above 12 inches. First, I use my index finger of my left hand pointing up the measuring tape to the 12-inch point, where I pause briefly, pointing at the boundary between these two parts of the measuring tape, and then change fingers and use a second sweep up the measuring tape beyond 12 inches.
Here, is this the ruler from the toolbox?
Yeah, this is from the toolbox.
Notice that, well, what do you notice here between the spaces here up to 12?
Now, in his response, he says the following: there's more. It's like it's more spread out when you pass 1 foot. And when you're before 1 foot, it's more. Now, by itself, his words don't provide a thorough explanation. But we're going to look at him speaking and using his gestures. And in fact, in combination, he provides a very comprehensive explanation of different attributes of the measuring tape.
Here, is this the ruler from the toolbox?
Yeah, this is from the toolbox.
Notice that, well, what do you notice here between the spaces here up to 12
Yeah,
and the spaces after 12?
There's more. It's like more spread out when you pass 1 foot, and then when you're before 1 foot, it's more.
Okay.
Now, in that 8-second interval of his explanation, maybe 9 seconds, there are 9 gestures that he uses. And so the first gesture, he uses the 4th finger of his left hand, and he sweeps up the measuring tape. The 1 foot mark is about here. He starts his sweep. In the middle, he does a chopping motion as if he were marking those marks that are on the, reinscribing the marks on the measuring tape, and then he continues his sweep up the measuring tape to 1 foot. Then he changes from the fourth finger of his left hand to the first finger of his, oh, I'm using, by the way, if you're a pianist, I'm not using pianist finger. I'm using violin player and wind player fingering, so finger 1, 2, 3, 4. He changes to the first finger of his left hand, still pointing at the boundary between the two parts of the measuring tape, and then makes a wide interval gesture. Remember, the intervals on this part of the measuring tape are wider, and then sweeps this up the measuring tape. And then to reiterate that, he makes a pinching motion across the measuring tape at a foot, and then sweeps this pose up the measuring tape. And lastly, and I went frame by frame, and I caught a frame of him coming back in referring to the part of the measuring tape below 1 foot, and actually he made the wide interval gesture above a foot. He makes a small gesture with his hand in referring to the region of the measuring tape below a foot. Now, these are significant parts of the theory of knowledge objectification, and exemplified in this clip are two things: iconicity and semiotic nodes. Iconicity refers to times when you reenact something you've experienced. You bring, I have a much nicer definition. Let me read it. Iconicity is the link between past and present action. It refers to the process of noticing and reenacting or revoicing significant parts of previous semiotic activity for the purpose of orienting one's actions and deepening one's own objectification. There are three forms of iconicity here. C is reflecting the kinds of gestures, changing fingers, pointing to the measuring tape that I used. He is reflecting the markings on the measuring tape with this chopping motion. He also represents he first represents the intervals above 12 inches with a wide interval, and I would argue then by coming back and using a small interval gesture is mirroring what he had just done himself in the context of the intervals below 12 inches. Semiotic nodes are places in mathematical activity where multiple semiotic systems are used together and in a coordinated manner to achieve knowledge objectification. Since knowledge objectification is a process of becoming aware of certain conceptual states of affairs, changes in semiotic nodes are associated with the progressive course of becoming conscious of something. They are associated with layers of objectification. So the way we use semiotic systems together and in coordination is by paying attention to that, we can track development in the objectification process. So at this stage, C is using gestures and mostly gestures and a few words, and by tracking their use together, their coordination, and the balance of gestures to words, we'll now track his the development of his understanding over the course of the tutoring session. So pay attention to the way that C's use of gestures and his use of language become coordinated with one another, as well as the balance of one to the other in their combined use. So 15 minutes later.
Also, then little ones, all the little ones are, if I have 3/16, and I would just count, if I have 1 inch and 3/16.
So his gestures are quieter. They're quietening down, but he's using them in coordination with his speaking. A minute later.
So if it was 30 seconds, then you would count the little small ones.
Yeah. Yeah.
Okay.
See, he's counting them and pointing to a phantom ruler there with his left hand. Explaining his reasoning for 30 seconds. This is 6 minutes later.
Each little interval is how much?
This is 30. You said it's 30 seconds.
Yeah.
Right? From like if I would count everyone would be 30 seconds.
Yeah.
And then you said the next one would be every 16.
Yeah.
So every second one's 16.
Yeah.
Now here his gestures are serving to make clear what he's talking about. He's pointing to the things that he's talking about. And 2 minutes later, he provides a comprehensive explanation of the pattern he's seeing.
Like now I understand it, because now every 2 would be 16ths, every 4 would be 8ths, every space would be quarters, every 2 spaces would be halves.
Okay.
Notice he saw quarters. He called them spaces. He changes the way he talks about them. So he had a multiple reference, and yeah, I'll leave it at that. So the analysis from clips 1 to 5. C's manner of expressing his thinking about the fraction of an inch pattern on the measuring tape using various combinations of semiotic systems changes considerably from a predominantly gestural approach with minimum use of language to start, to speaking more clearly and succinctly with gestures playing only a supporting role for his verbal explanations by the end. As I mentioned earlier, or I explained earlier, Radford calls this feature of knowledge objectification, the knowledge objectification process, semiotic contraction. Our means of expressing and thinking about mathematical objects becomes predominantly language based. Other findings. Now, this wasn't in the clips, but based on the entire session, C repeats or reenacts what I have just said or done relating to the task on actually more than 60 occasions, at least 60 occasions during the duration of the interval. So the attunement and I also, on a few occasions, I reenact or repeat what he says. So there's a close, there's close attention to one another, and this is not the same kind. It's not. I wouldn't call it iconicity because it doesn't relate to mathematics, but it's a way of still mirroring what's said for the process of keeping us in tune with one another. Over the duration of the tutoring session, L's use of multiple semiotic systems in a coordinated manner while expressing his thinking remains relatively consistent. This reflects the stability of his objectification of the fractions of an inch pattern on the measuring tape. So if these changes reflect developing objectification, increasing objectification, then it's not a surprise that yours truly, who's been doing fractions of an inch since elementary school for decades, isn't changing in the course of this 33-minute session. Now, a few words about the dialectical relationship between objectification and subjectification in mathematics learning identified by Radford. Subjectification is the process of becoming in activity. Now, we become participants in activity, we become positioned in activity, and so there's a back and forth, there's a give and take. As we learn, we change. And Radford calls this process subjectification. Now, this column refers to C's objectification. This column is objectification, C's objectification and mine, because within activity theory, I'm a participant and need to be acknowledged within the activity, and the subjectification is here for both of us. So C becomes aware of and conversant with different aspects of the mathematics crystallized within the pattern of markings on the measuring tape. He becomes able to read fractions of an inch to 16ths. Now, well, his objectification is developing, he too is changing. He becomes a more active participant within the discourse with L, as evidenced by changes in the patterns of his gaze and attentiveness, seeking clarification from L, expressing his thinking, setting tasks for himself to complete instead of depending on me to lead him through the session, and offering up assessments of his own understanding and a sense of agency relating to his use of the measuring tape. He becomes confident in his ability to read the measuring tape and his ability to use it to successfully carry out the practical work required in his training program. Now, I changed as well. I became attentive to the practical needs of measuring activity in the workplace. At the beginning, I was basing my, the strategy to read fractions all on whole inch and working down from there, because I knew from working in a machine shop that there are different kinds of rulers or measuring tapes. In a machine shop, there are rulers that measure that are marked to the nearest 64th, marked to 64ths of an inch, and measurements are in some cases taken to the 64th of an inch. This ruler, this tape measure was marked to 30 seconds, and of course there are, we've all encountered rulers or tape measures that, that are marked to 8ths or 16ths. So I came to this tutoring session with my math educator hat on to provide the most generalizable approach. I became more pragmatic in my approach to teaching C. I became a more genuine mathematics educator when I realized that, you know, after struggling with this, he only needs to use 16ths of an inch. So what we did, if we were measuring a length, I directed C to start at 10 inches so that the end, the terminal point of the interval being measured is in the area of the measuring tape that measures in 16ths. Now, I confirmed with a number of instructors in the pipe trades, because I was an outsider to the pipe trades and pipe trade practice. I asked if that would be an appropriate thing to do in the workplace, and they emphatically agreed that that's the kind of thing you do to get the job done. So that was fine. In fact, I caught myself when I started to instruct C to use this approach. I caught myself saying, "Well, let me show you a strategy. It's kind of cheating." Signaling that I was crossing that cultural barrier. I was going where no math, no self-respecting high school math teacher should go, to give students an easy way out. So implications for teaching mathematics in workplace training. There are lots of implications, and I welcome your thoughts. I think there's a vital role for face-to-face social interaction. There are some workplace programs that plunk students down in front of computers or videotapes and expect them to learn mathematics. It's very much a give and take. It's not just the information, the words. It's the body language, it's the gestures, it's the responding to one another. That's an important part of this process as well as the use of workplace artifacts and doing it on the job. Doing mathematics and supporting students with having difficulty within the context of workplace training. The folks from SkillPlan had their tutors in these apprenticeship classes. Now, it would be unusual, I think, to have a math tutor designated to a specific trade or training in a specific trade. But if they're in the class and seeing what's being done and how it's being done in class, they can support students within that context so that there's no mismatch between what the tutor is saying and with what's being done in class and the work being done in the workshop. It's also a good way to get students who are having difficulty in apprenticeship classes to come to get some extra help at the coffee shop afterwards if they've already established a relationship with their tutor in class. I think too, there's a need for coordinated efforts of both workplace practice experts and mathematics educators to develop and deliver workplace training. This includes investigating workplace mathematics practice and learning to find and create ways to help students having difficulty. Now, I brought something to the table sitting in these classes that wasn't there. Ways of unpacking mathematics so that it was easier for students to recognize patterns. But the whole workplace practice, the feel of the mathematics, using workplace tools, workplace conventions was not my area of expertise. So I think there's a need for a collaborative teaching between mathematics educators. It means we have to move out of our comfort zone to do math in ways that are unfamiliar to us, along with workplace trainers. Just some examples. My pipe cleaners are still in my suitcase in Anne's guest room. So I'll explain what I did when we were doing this in class. We were unpacking the mathematics, semiotic extraction, a term that I've coined to talk about the process of a math educator pulling out the patterns so that students see particular cases as instances of something larger. Deborah Ball talks about the need of math educators to unpack the mathematics. So within the context of Radford's theory of knowledge objectification, I call it semiotic abstraction. So what we did, I started with a pipe cleaner in this configuration, and just the pipe cleaner, so we could work on it flat on the page in 2 dimensions. And we did our calculations. And then I used pipe cleaners to construct both this triangle here and this one as a 3-dimensional model. And it helped students to see more clearly what was going on. They needed that in 3 dimensions before they could read a representation of 3 dimensions that's only in 2 dimensions. So I gave them that 3-dimensional model. Ironically, I left it at the pipe trade school on the weekend, and they had cleaners in on the weekend, and the cleaners thought it was trash and threw it in the garbage. So I got good at making these models. Another example that comes out of the working with apprentices. Initially, after working with an apprentice in ironworking, I'd made a set of acetates. I took a ruler, I enlarged it. Well, I won't worry about the mechanics, how I got there. I took a ruler and I photocopied it onto an overhead acetate. And then I whited out the 16ths and photocopied it again. Then I whited out the 8ths, photocopied it again, and quarters, halves. So I had a series of acetates that superimposed upon one another. One with intervals in whole inches, then half inches, quarter inches, 8ths, and 16ths. And I was using that, in fact, in my interview with C to show how the different fractions are to be read as intervals on the measuring tape. We were doing a lot of sweeping between the marks. So what's interesting here is that the mathematical object, the interval, wasn't on the page. We had marks at each end. It was the thing between the things that were marked on the page that we were attending to. I thought, well, how can I point to the thing as opposed to the not thing, the interval rather? How can I point to those intervals? So I came up with an alternative teaching tool based on these sweeping gestures that pervaded the 33 minutes. And it was to get, so this is an enlargement. So the idea would be to start with, and imagine this is really 3 inches. We would start measuring objects with the top ruler, and the bars are the length. So we were able to point to the bars and not have to sweep between the markings on the page. And after we're successfully able to measure things to the nearest inch, the next line has half-inch intervals included, then quarter-inch intervals, 1/8-inch intervals, 16th-inch intervals. And after we're successfully working on various measuring in different subunits of an inch, we just take away the horizontal lines and then we have the pattern on the measuring tape. The point is, we need to see this as intervals, not as marks. And so this is, I haven't piloted it, but this came from my observations as an educator in the classroom and watching practice in apprenticeship training. So other implications for teaching and workplace training. What do you think? So I'm done the formal part of my presentation. I would love to hear any thoughts you have. Certainly we'll have questions, but if you have any thoughts on where or how this might apply elsewhere, I'd love to hear what you think. Sir.
Sign language is recognized as a bona fide language. It seems to me that the gestures could be sort of like an ideograph of sign language, and maybe could even be fine-tuned formally. And there are all kinds of possibilities. Yeah. But what he was doing intuitively was just wonderful.
You know, formal language has a syntax where we didn't have that.
That's why I say ideograph.
Yeah.
It's sort of a subset of the language.
Yeah.
Like mathematics.
And along the way of language, you know, I was thinking about isometric projections the other day and thinking about what it takes to read that. And there's a literacy there to read a 2-dimensional representation of a 3-dimensional object. That's only a small part of geometry and spatial sense in mathematics. There are many other, math is like a number of languages. And so we have math as a number of languages and ways of seeing the world, the ways of expressing those ideas. And I'm suggesting then we have different genres of those in different contexts. So it's the categorical claim or description of mathematics as a language, I think, is far too simplistic. Anne.
I'm thinking of the ruler that you just created, the one on the previous slide, and going back to, we had a discussion this afternoon where we were talking to somebody in one of the trades talking about precision. So I looked at this and started thinking about how it might be a tool for unpacking some of those ideas about precision and what it actually means.
Thank you. When we learn to use a measuring tape, we need to also talk about tolerance. How close is good enough? We often don't talk, in our curriculum in Ontario, we don't talk about that when we do measurement. It's typically drawings on a page in the textbook. The numbers on the page are the ones you need to use, and just add them up or multiply. You know, the idea of close enough, so you should be able to, on the whole inch ruler, eyeball that to the nearest half of an inch. Okay. What a nice lead-in then to move to the next ruler. So the idea of needing different tolerances or margins of error in different contexts needs to be part of our measurement discussion with students. Just a story from my work with my dad in his machine shop, I did a small case study of his mathematics use for PME&A some years ago. You know, the units of measure in a machine shop are thousandths of an inch. And he had a job for special bolts for a nuclear reactor that needed to be to the nearest 10,000th of an inch. And they are so precise that once you've used the bolt once, if they need to take it out, they have to throw it away and put a brand new bolt in. And so there was some fancy grinding involved. And even in that context, he talked about it not in 10,000th of an inch, but a tenth of a thou. And if you talked to, he wouldn't ever say 100th of an inch, it would be 10 thou. And he makes reamers, which are a cutting tool for making holes of precise size. And they're stamped, you know, 3/4 of an inch plus 3 thou, 0.003 of an inch. So fraction or notation and decimal notation on together. And he related to me in depth how the different sizes above and below, in this case 3/4 of an inch, meant it felt differently when you either push this into a hole by hand or pressed it in with a mechanical press. So an example of that feel related to measurement. Any questions? Sir.
I'm curious as a mathematics teacher, if you covered the mathematical relationship in the intervals in this, because in the workplace it is, get it done, you need to understand what the intervals are. Did you ever cover that a 32nd is 1/2 of a 16th?
We did.
And was that of value, or does it, for workplace, really just matter, these are the tools you're going to use, and so you just need to know the intervals?
We talked about how many per inch and counting, so that if C had a different type of ruler or tape measure in his toolbox on the job, he could determine the smallest interval. We did talk about the relationship between 32nds and 16ths, 16th and 8th, and so on. We ended up, C ended up using 16ths, the intervals on his measuring tape above a foot, as a benchmark, and he counted, he knew that 2 of them equaled an 1/8. He saw quarters in a distinct way, and he knew that 2 of those intervals were a half, and of course he understood whole inches. Now we also talked about, for example, if you're measuring 7/8, rather than identifying and counting up 7/8, counting back one. So in answer to your question, yes, but there were other things to reading the measuring tape as well.
been out on construction sites where people would just say, so what's the measurement? You go 5 inches and 5 little lines. So then you have to go, all right. So, and if you're talking over a walkie-talkie, then you have to say, so between the 5 inches and 6 inches, how many little lines are there? So you get a sense of what they're actually measuring.
One of the iron workers on occasion told me he was an experienced, this would have been, it was either a second or third year student. So he had been in the workplace at least for 1 year. And I talked to him about doing math on the job, and he said every crew has its steady Eddie. So the go-to person for doing the math. Now certainly you won't become promoted to a crew leader without the math, but not only are there different tools to use on the workplace, there's, you're working in a collaborative context, and so there is a division of labor amongst folks working together. When I followed the HVAC folks around, they had their cell phones. They were working by themselves, but they were in touch with one another about technical details, about information. And I think it raises an interesting point about mathematical competence for work. I'd rather someone not know, but know they need to call and know who they need to call, than someone who has it right most of the time, but really doesn't know if they're unsure or if it matters.
I'd like to share, I actually worked for Habitat for Humanity on the Mississippi Gulf Coast, and we drew that out, not fully detailed, but at least an inch worth, and then all the fraction breakdown next to every single chop saw with, in parentheses, remember the thickness of the blade of the saw is 1/16, which a lot of people don't know. And so we would tell them, be sure to incorporate that measurement in addition to whatever number we tell you to cut. And by the end of the day, there would be so many, math sketches and drawings right next to the saw that at least we knew the people were working it out or trying to make it work.
Now that would be a very cool dissertation or master's thesis, by the way, if there's any graduate students here. That would. There was another point I wanted to. Oh, it'll come to me. Okay. Yeah.
Did you talk to any of the people, or did they volunteer any comments about their memory of doing mathematics at school?
Yes. I was privy to the entrance, the information for admission to the pre-apprenticeship program. The vast majority of candidates had grade 11 academic math, which there are 3 years of math required in British Columbia, and they inevitably, or the great majority of them had taken academic and done very badly at the grade 11 level and then stopped taking mathematics. So of course there were students talking about a lack of confidence, about negative experiences. That's part of that subjectification that happens in school mathematics that we need to overcome.
Tell us a little bit about C. Who is he? What is he like?
Yes. C was, had been out of high school. He was a high school graduate in British Columbia, had lived his entire life in British Columbia. He had spent, had done some courses in an electronics technician training program at college and did not complete that program. Had been in the workplace for a couple of years and was in this program looking for a chance to get a good job. He was, even within the first week, was a regular. I set up a help table at the back of the classroom. So when students were doing their work, if they wanted to come and work at the table, just to be close to someone else, they could ask a colleague, they could ask for help, or to get help from me, they were welcome to. So I usually had a gang of men and women at the back table. They worked together. C was a regular, and he sought me out regularly. So he was particularly open with me in terms of sharing his thinking and seeking help.
I don't know if I have a question, but I think a lot about mathematics outside of school and in school too. And one of the things that was really striking about the video was his use of gesture, as you pointed out. And I'm thinking, last week we had a talk about the difference between the cognitive and sociocultural model of learning and what that means for education. And I was thinking that in school mathematics, we have this image of like all the knowledge residing in a student's head and then coming out in either what he or she writes or says. And looking at that, it just made it very visible how much of the mathematics was not in the head, but it was kind of out with the tool, with the gestures. And that, I don't remember your distinctions between school mathematics and mathematics in the workplace, that was one of the distinctions, but it seems to be huge, that the mathematics isn't residing in just the head.
And was C even aware of the details he was articulating with his gestures?
Right.
I think another way to look at iconicity is it's a way of extending one's experience of the signs that you're working with in part of the objectification process. Objectification is a refinement of Vygotsky's notion of internalization. Radford's work is rooted in the work of Vygotsky and Leontiev, and so it's a more refined concept for mathematics learning. Yes?
Were there aspects in the training that were like algebraic in nature at all?
There were formulas to use for various computations. Certainly there were measurement formulas that were used for area and volume. There were even I'll go back to the example of oh, it's not here on the page. The page that this was taken from had formulas for taking values from this table, the fitting allowance and the thread makeup, and then the takeoff was the amount you would chop off the pipe. So the diagram would say from here to here is 8 feet, and then if it was fitted on each end, there'd have to be a compensation for the threading. And so there were formulas there. In calculations regarding conversion, things like horsepower, flow rates, there were typically 1- and 2-step algebra substitution types of things. That was about the extent that I saw in levels 1 and 2 of the pre-apprentice, level 1, let me back, in the pre-apprentice program that reflected the mathematics of levels 1 and 2 in the formal apprenticeship program. In the higher levels, there was limited formula use in the 4th year, mostly formula substitution.
Can I just add to that? Was there any, in reference to the algebra world, reliance or but like use of equivalence as well?
You're talking about fractions or fractions decimals or?
Any and all.
Well, certainly.
I mean, there's a lot of places that equivalence shows up here.
Yes.
And I didn't know if it was like brought out and recognized or if it's just kind of.
I don't think the word ever came up. It's a convention in the workplace as it is in school to work in lowest terms with fractions. Converting between fractions and decimals was common between different units of whether it be volume, area. Typically not between metric and an imperial measure, but between, for example, gallons and cubic feet. Cubic feet and using density to find mass of objects being supported, but not sort of mathematical equivalence. It was typically for the purpose of calculating something for a workplace, some form of workplace production. The details of the mechanics really weren't on the table, and I'll say the great majority, if not all, the instructors were not concerned with how students found their answers. And to their credit, they encouraged students to help one another. So students were working collaboratively.
Were calculators used a lot? Oh, sorry.
Go ahead.
Were calculators used a lot?
Students had calculators. It's interesting. The materials were written some time ago, so they weren't designed for students whose calculators did fraction computation. So there were some students who had whose calculators did fractions, and no one paid attention to the kinds of calculators they were using. I don't know if that there are any restrictions about the kind of calculators that are used on the Red Seal exam that comes at the end of 4 years of apprenticeship training that allows you to work across jurisdictions. And the worksheets were not designed to be used with calculators. So the students were able to work their way through this without really grappling with the mathematics at times. And this is where something a math educator would recognize and where their voice would be important at the table.
As a math teacher, one of the things that I try to do a lot is to take the intuitive ideas that students come in with, yeah, and allow them to see the correspondence between that and what they're doing. Like, for example, you were mentioning tightening a thread. Do you have any situations where you actually give a student a torque wrench and let them feel what it's like to strip a thread?
It didn't occur in what I observed. In ironworking, unlike, say, the automotive industry, you're not going to strip a thread by hand. They're big bolts that hold girders on skyscrapers. One model, well, a scenario that was done with the ironworkers was to put slings on a beam. If the support slings, they're wire rope, are put at different angles, you get different tensions in the sling. And so they had a crane and a crane operator in the yard, and different the beams were lifted with the slings at different angles, and they had a force meter in the configuration, so they could actually see the effect of the difference in forces. But I think you raise an interesting point there. We want to explore the possibilities to really get it. That's how you get a feel for it. Certainly using a micrometer, which measures to a nearest thousandth of an inch, there's a feel to getting to knowing to getting the same measurements as the machinist who's an old pro.
We'll make this our last question then, okay?
We have the advantage of having work sites. We actually build affordable housing.
Yes.
So the students spend half of their time in classrooms and half of their time on actual work sites. So they definitely get the feel for whether a measurement is right or not. They put it up on the house. And short again, I measured it twice, you know. So they really know what that's like. And my job is to prepare the students as well as I can to go out on the site and measure properly. And for anyone that wants to know, after 13 years, my silver bullet is something called the ruler game. Go on Google and you go to the ruler game, and they get you to practice over and over and over again, making these measurements right, wrong, right, wrong. Finally, they get it. Most.
Let's thank our speaker.
Thanks for coming.